Hello everybody, my name is Masha Brodanovic and we're going to do a review of linear algebra. So this is for PG 310, Formulation and Solution of Geosystems engineering problems. Our objectives in this review is to review basic operations done with vectors and matrices. This includes how to add, subtract, multiply vectors and matrices, create transpose of vectors and matrices, create and recognize linear combinations of them, calculate inner product of vectors, determine whether they're orthogonal or orthonormal, and use vector norms to compare vectors. We will also name some special types of vectors and matrices, and we will do this both by hand and using MATLAB. Related reading is in our textbook in chapter 8.1. So let's get going with vectors first. And this first video will be on vectors only. Vector is an ordered set of real or complex numbers arranged as either a column or a row. So here we have an m by 1 vector. That means that I have a column. Technically, this is a matrix as well that has m columns and m rows and only one column. So I have essentially m numbers just arranged as a column, whereas here I have a row vector. Its official dimension is 1 by n, so I have n numbers arranged as a row. Our notation for this review will be that we will use lowercase Greek letters, alpha, beta, gamma, and so forth, for scalars, lowercase Roman letters, u, v, x, y, b, for vectors, and uppercase Roman letters, such as ABC here for matrices. Now this is simply to simplify typing. We will do this in MATLAB as well, so this is probably slightly different from the notation we used in other classes that review linear algebra. Now, vector operations typically need both vectors, if we have two vectors, both vectors in question, to have the same number of elements, and technically to be also the same arrangement, so either a row vector or row vectors or column vectors. So here, for instance, we have two vectors. First one is 2, 1, 0. And the second one is -1, 1, 5. So if we want to add these two vectors, what we will do is simply do it element by element. So we will simply perform this operation on corresponding elements. So the result of the addition will be 2 minus 1. There will be 1 here, 1 plus 1, 2 here, 0 plus 5, 5 here. Okay? So we can do addition and subtraction in the very same manner. Now, we can also multiply entire vector by a scalar, in which case we will multiply every element by that same scalar. And we can transpose vectors, in which case transpose of this vector, which is a column vector, will become row vector, and transpose of a row vector will become a column. So let's just explain this a little more in a more generalized way. If I actually have two vectors and I have two scalars, alpha, beta are scalars, and u and v are vectors. If I'm going to do a linear combination of the two of them, then I'm going to multiply elements of the first vector by alpha and add them to the corresponding elements of vector b multiplied by beta. Now, vector inner or scalar or dot product, so there are three names for this product, works with two vectors that have the same number of elements, and the result is always a scalar. So basically what we do is we take corresponding elements, multiply them, and then sum up all such multiplications. So this symbol here, sigma, is symbol for a sum. So I have sum over all of the elements from I to n of products xi times yi. So for instance, if I actually had two vectors with 4 elements, this would be x1, y1 plus x2, y2 plus x3, y3 plus x4, y4. This can also be visualized as a form of a matrix multiplication of a row vector by a column vector. So I'm again going to have a corresponding multiplication as x1, y1 plus x2, y2 plus x3, y3 plus x4, y4. This is precisely how we will do matrix multiplication, and we will review this in a little more detail later. So for now, it's important to remember that inner scalar or dot product is the sum where I sum over all of the possible combinations of the multiplied elements x1, y1 plus x2, y2 plus so on. So let's now do an example, and I'm going to switch software from PowerPoint to Sketchbook so I can actually write and show you an example. So if I'm actually looking a little off the screen, that's because I'm actually using a separate tablet for this purpose. So in any event, let's say that we have two vectors. The first vector is u, and it is 3, 2. This is a column vector, and its size is 2 by 1. Okay. And let's say that my v vector v is 1 minus 3. Okay. So let's, for instance, have a linear combination with coefficients alpha, where alpha is 2, and beta, where beta is, let's say, minus 1. What would my combination W, which is alpha u plus beta v, look like? Well, it's 2 times 3, 2, minus 1 times 1 minus 3. When I do the corresponding operations and add the elements, I'm going to have 2 times 3 minus 1, which is 5, and 2 times 2, which is 4, plus 3, which is equal to 7. Okay? So this is the linear combination. Now let's do some other examples. For instance, can I do an operation 3, 2, which is my vector u, plus number 2? Formally, I cannot do this because this is 2 by 1 vector, and this is a scalar, which is actually 1 by 1 vector. Scalar is a 1 by 1 vector, so this is not possible. We will see, this is just a quick note, that this is something that is going to be possible. Just a moment. I will change color. So this is possible in MATLAB though. So in which case MATLAB will actually add 2 to each of these elements. That's simply a shortcut in MATLAB, mathematically not possible. Okay. Now let's say that I actually also want to formally add something like, let's change colors here, 3, 2, which is my vector u, plus a vector that also has 2, 1, 7. So this is a 3 by 1 vector. Again, I cannot do this addition. Do addition because dimensions do not match. Okay. Also, even if I actually technically have the same number of elements, such as if I do transpose of u, which is 3, 2, if I want to add that to my vector v, which is 1 minus 3, formally I cannot do this because my dimensions do not match. Okay. However, what I can do is I can actually do dot product. So my u dot v is also formally defined as u transpose v, which is 3, 2, multiplying 1 minus 3, and that is equals 3 times 1 plus 2 times minus 3, which in this case is equal to 3 minus 6, which is minus 3. Okay. So this is some examples of these vector operations. Now let's move on to vector norms. Oops. Okay. So now we will quickly move on to norms. So my vector norms compare the sizes of vectors. So we will actually have unit vector, it will have a magnitude 1, and zero vector will have a vector magnitude 0. We know in regular numbers, absolute value is a measure of a magnitude. So I will, for instance, number minus 3 has magnitude 3, so I can compare magnitudes of vectors as opposed to just vectors themselves. And norm is doing the same thing for vectors, and we will typically, to distinguish the two, we will mark absolute value with single line and norm with this double line. So this just basically tells us that we are operating on vectors. Okay? So what are some typical norms? First one is Euclidean, or so-called L2 norm. In 2D and 3D is simply geometric length. Okay? So, but I can define it in any dimension, in which case it's going to be, this is square root of sum of squares of all of the elements of a vector. This can also be expressed in terms of this inner product. Okay? So inner product of a vector by itself is x transpose x, and square root of it is the Euclidean norm, or norm 2, L2, of a vector. Now I have some other norms. There's not just one norm, and for different situations we will need different types of norms. So in most general case I can define a P norm. This is possibly slightly too mathematical and too abstract, but I could have L1 norm, which is simply summation of absolute values of all of the elements, and I could also have L infinity norm, which is simply the maximum of all of the absolute possible absolute values of the elements of a vector. So let's actually do a computation of all three norms for vector 1, 2, and I'm going to switch quickly to my sketchbook again. So let's do my vector. Let's define a vector 1, 2. Okay. So that is my, I'm just going to name it differently. Let's name it x. So what is going to be my norm 2 of x? It is square root of first element 1 square plus second element squared. Okay. So this is square root of, in this particular case, 5. Okay. And what I said is that this is equivalent to basically square root of x transpose x. So that is square root of x transpose is 1, 2 as a row vector, multiplying 1, 2, which is again the same thing, 1 times 1 plus 2 times 2. Now we already computed it, that is overall square root of 5. Okay. What is the norm 1? By definition, it should be in a vector that has only two elements, absolute value of the first element plus absolute value of the second element. First element is 1, second element is 2, so this is 3. And norm x infinity is simply looking at the maximum of all of the absolute values. Whoops. X2, which is maximum between 1 and 2, and that is it to 2. Okay? So if you look at the Euclidean norm, the point I made is that in 2D or 3D, this is simply a geometric length. So let's just quickly look at that in my x1, x2 plane. So if I had vector 1, 2, this is my vector x. Okay? So this is simply length of this line here would be precisely square root of 2 based on Pythagorean theorem, right? Because this is 2, this is 1. So if this was a velocity, for instance, of an object, then magnitude is essentially speed. So speed is magnitude of velocity vector. So this would be one example where my Euclidean norm is actually a physical value of speed, which we use in daily. So these are the examples of norms. Now, what would be a unit vector? How would I get a unit vector that is in the same direction as this velocity vector here? Well, I would simply, I'm going to call this unit vector x. I'm going to simply divide my vector x by its length. Okay? So basically this is going to be 1 over square root of 5 of 1, 2 in this case. And since I divided it by its length, the length, geometric length, or in this case the norm of this vector is going to be -1. So unit vector has magnitude or norm 1. And this is very ugly handwriting, which is, I should better stick to PowerPoints. So unit vectors have a norm 1, and only really a 0 vector has 0 norm, so my 0 vector is the only such element. Okay, so let's go quickly back to PowerPoint to continue the review. Okay, so some properties of vector norms are as follows. We have that norm is always positive. Okay? If I multiply a vector by a scalar, then the norm of that new product is the absolute value of that scalar times the vector itself, norm of the vector itself. And there's so-called triangle inequality. If I add two vectors, the norm of such an addition is always less than or equal to sum of the norms of the individual vectors. So all vector norms, regardless of the type of the norm, actually have these properties. Vectors are orthogonal if they, in 2 dimensions, they're simply perpendicular, so they form a 90-degree angle. But we can actually use norms or L2 norm to look into that. So two vectors are orthogonal if their dot, inner, or scalar product, remember that we have 3 names for it, is 0. Okay. So we can actually figure out whether two vectors are orthogonal in the plane based on simple formula. We just find their scalar product and see whether it's 0, and in that case we know that they're orthogonal, but more generally this is how we actually find the angle between two vectors. So and this is finally just a quick definition of those orthonormal vectors. Those are unit vectors that are orthogonal. Okay? So let's actually now quickly check whether 1, -1 and 1, 1, two vectors are orthogonal. Okay? So if we do, we will first check their inner product. So 1 times 1 plus -1 times 1 is equal to 0, and therefore they are orthogonal. You could actually draw them in the plane and see that they actually form a 90-degree angle. Now, how would I convert either of these to a unit vector? I would basically divide by a norm. So norm of, for instance, this second vector, 1, 1, is square root of 1 plus 1, so square root of 2. So I would simply divide this entire vector by square root of 2. So my new unit vector would be 1 over square root of 2, 1 over square root of 2. And that's essentially ending our quick discussion on vectors, and you're supposed to do a quiz after this video.